Hello, it's your dev dog here. Ruff. I recently finished playing God of War, replaying God of War. There was this one effect that I really liked, and it was this fast travel sequence. You go up to the door, and then you hold up a little thing, and then it rebuilds the door in front of you. And of course, probably the easiest way that you would do something like this is to actually have it animated inside of like Blender or whatever, and then importing those animations, and that would be a lot more performant than trying to do it physically based inside of the game engine. If that's what you're looking for, render it out in your animation software with physics applied, and then just reverse it, and that's how you would get that effect. But what if we just wanted to have like a 3D model or something, and then go through all of it and sort of recreate this effect? So what I have here is we're gonna do today is this door summoning effect. So we have an empty scene, but then we have a pile of rubble, and if we get close to it, you'll see that, oh, it rebuilds itself. And then if we leave, it sort of collapses. And this is all physically based, so we can actually interact with the boxes, and they do fall in different ways. So it's not going to fall the same way every single time. And just depending on how close you are, it will rebuild itself, and you have these nice little deviations of how it fell from the previous time. Let's go ahead and get started doing it. What we have over here is very simple. We have a script. I already wrote out the script, but I'll go ahead and write it out again with you here. So this is our door summon class, and we're going to have to do a few things before we even get started with that door. If you already have a model, all you have to do is actually separate out that model into separate pieces, and then have it under one parent, but just under separate pieces. So if we look at all these boxes, they all have a box collider. And if you had your own 3D model, you would either do like a box collider or capsule collider, something that makes sense to conform around each shape, or you could just do a mesh collider to have like the most realistic interactions between everything. But that's really performance heavy, so it would probably be worth it to just go in and try to get in a box collider or a sphere collider or a capsule collider, something to make that performance a little bit better. In order to make this door, what I did was I just created an empty. So we have our empty, and we could call this door 2. And then inside of this empty, let's go ahead and make our boxes. So we have cube. Let's reset this. Reset. Was that where it's at? Okay, let's lower this door a little bit, just so it's on the ground. And then let's go ahead and let's do, 4 is fine. And then let's duplicate it, and let's do -4 on this one. And then we can, it's going to be a bigger door. That's fine. We're going to just duplicate these again, and then raise it up a little bit, and then duplicate it again. And just however many cubes you want. It really, the way I programmed it really doesn't care which way or how many doors or how many boxes you want. And, if you wanted something more grand, you can do that also. And then here is our door. This is how it's going to look like when it's rearranged, and we can adjust it a little bit so it's not as far apart. But maybe you might like that, actually. You might like that it's far apart. Oh, whoops. Let's go through all of these, and we could just shift-click all of them, and then add a rigid body onto them. The very first thing that we want to do, if we go into our door script, we have everything set up already. We have all of our door pieces with a box collider and a rigid body. The first thing that we want to do is we want to track the position and the rotation of all the children, right? This is step 1, because we can't rearrange it unless we know where it originally is at. Then once we have that set, we also want to destroy the door, right? So we want to destroy the door. In order to destroy the door, and we want that randomness built into it, we have to have some sort of force applied to each piece of the door. In order to apply that force, right, we're going to have some sort of random force. We also want to determine how long it should take for the door to be rebuilt. And we could just have that under like a really quick float, right? A random, or it could just be the rebuild duration. And then we also, this is like an added feature where we don't want everything to sort of come back together at the same time. And if we look at this animation, okay, this door fell. If we look at this animation, you'll notice that not everything comes back at the exact same time. Some things are delayed, some things go back faster, some things go back slower, and it's very subtle, but it is there. Like we see a little bit of that delay with each individual piece. You know, if we wanted to add that feature, we can go ahead and add in sort of like a rebuild duration offset. So this is just going to offset the duration of how long it takes to build a door. And in order to track the positions and the rotations of each of these, we also want to keep an array of all of that. So in order to hold an array of all of that, we need two different arrays. One array for vector 3, and this array of vector 3s is just going to be all of our initial positions. And then we also need the exact same thing for the rotations. And in order to hold a rotation, you want to hold it inside of a quaternion. And this is going to be our initial rotations. So we have our initial positions and our initial rotations. And another thing that we probably want to get a hold of, whenever we want to apply this random force to each child, we have to have a way to reference each individual rigid body and to iterate through all of the children and find each individual rigid body multiple times in order to run this one method of applying this random force is going to be really costly. So instead of trying to find it each and every single time, we can just also have the rigid bodies, an array of rigid bodies, and we can have that as like the door piece rigid bodies, right? So if we want to iterate through all of them and apply a force, we can just go through a for loop instead of trying to go through and find them each and every single time. We also want a way to figure out, here, let's go ahead and delete this update. Because I think, I know we're not actually going to use it. We want to find a way to track if the player is close enough to trigger the door to start rebuilding itself. There's a lot of different ways you can do this. You can do this inside of an update if you want to do it inside of an update. Probably the simplest way to do this would be to actually set up a on trigger enter to rebuild the door. And then we also want, when the player leaves, we want a way to like destroy the door again. We can see that we want to destroy the door twice, right? We want to track everything in the beginning. We only have to track it once, but we do again want to track the door. So we can go through and actually let's solve this problem of trying to track the positions and the rotations of all the children, and also now the added optimization technique of tracking all the rigid bodies. A very simple way to do that would be to just get the child count. We're going to get the child count of our transform, which is going to be the parents, which is holding all of the boxes. And we could just literally just get the child count. And because we now have the child count, we already know the size of each array that we want to make. So we don't have to resize the array, which is also performance heavy, or it takes a little bit of a hit for our performance. Let's go ahead and make each of our variables that we want to hold are both of our initial positions. Then we have a quaternion, which will hold our initial rotations. And then we also want to hold rigid bodies inside of an array, which holds all of our rigid bodies, our children's rigid bodies. And we can, instead of assigning them above, because we don't know how many children we're going to have, we can initialize them inside of the start. So inside of our initial positions, we're going to create this into a new vector 3 array of child count, because this is how many spaces that we need inside of this array. And we can do the same thing for the other two arrays. Okay, so we have that set. This is just setting up our logic, but we actually have to go now and assign each one. So in order to do that, we can just go ahead and make a really simple for loop. And we're just going to set this to 0, going to iterate until we're below child count, and then we're going to iterate once through, just so we can obviously get all of our positions and rotations for each individual child. Let's go inside of initial position, and we're not creating this. We're just assigning an empty field inside of our initial positions, and we're going to have to access the child multiple times. So for each child inside of our transform, we can go ahead and get the transform child by getting transform dot get child, and we're just going to be looking at the I position, and then get the position of the child, then get the rotation of the child, but just doing child dot rotation. And then we're also going to be getting the rigid body, which we should have assigned when we created our scene, right? Rigid body. Now we have reference to literally every single child with rigid bodies and everything inside of here. And now that we have everything tracked, the next thing that we want to do is we want to destroy the door. Let's go ahead and spread that out into its own method just to keep things a little bit organized. And we're just going to call this probably something like destroy door, or whatever name you think is appropriate for this. Maybe like apply random force. Now this is going to be fairly simple. It's going to be a little bit long. So we're just going to make another int, another for loop. And instead of iterating through all of our children and trying to get everything, because we already have our rigid bodies, we can just go through all of our rigid bodies, get the length of it. And once again, we're just going to iterate by 1. And then we're going to get the rigid body of our children. And we're going to set that to rigid bodies I. And then for each rigid body, we want to set it because when we rebuild the door, we have to set it to kinematic is true. We want to make sure that that is no longer true anymore. So in order to do that, we just get rigid dot is kinematic is equal to false. Now we never set it to true yet. It has been false the entire time. But when the door is being rebuilt, we don't want it to fight against the physics of the Unity engine. So we're going to set it to true when we actually start to rebuild the door. And whenever the player is close to it, we also don't want physics to interact with it. So as long as our player is within the trigger collider, we want this kinematic to be true. And just thinking ahead, if it's going to be true, we want to set it to false when we destroy the door. As well as doing that, we also want to apply a force onto our rigid body. Now, in order to apply this force, we need a vector 3 in order to figure out where we want to go. And because we have a random force, we don't necessarily want individually set the X, Y, and Z positions for the vector 3. We can just use the same random force float value and just put it inside of a random.range method to get a random range between negative random force and the positive random force. So in order to do that, all we have to do is we have to serialize this field so we can access it in the inspector and then set this as a float and get our random force. Now that we have that random force, we can do random.range, and then we're going to do negative random force, and we're going to do positive random force, and we don't need the plus, we just need to do random force without the negative sign. And we're going to do that basically 3 times, because in order to get the random force for the X, the Y, and the Z positions. Now, the final thing that we have to do is that add force automatically defaults to the force mode, or the force mode of force, I think. Yeah. Force mode of force, which is to add a continuous force to the rigid body. And this is going to be the default value. And if you don't set this automatically, it will be force, which is fine to have a force added continuously if you want to do stuff like movement. But we don't want to do movement. We want to have a force mode of impulse, which adds an instant force onto the rigid body and puts all of the force that would be put over a period of time into a single moment. So we want to add force mode impulse. Now, after we have that, we are going to destroy the door. Now that we have tracked everything, we can just go ahead and call destroy door, and this will automatically destroy the door. If we go back to our door 2, you'll see that we don't have a collider on it or anything to say that, any way to track how close the player is. So we can go ahead and add that, and you can add any type of collider that you want. I'm just going to add a box collider, or a sphere collider, I think is more performant. So we will add a sphere collider, and we'll make this however big we want our range to be. Whenever the player gets close within this range, then it should trigger this to start rebuilding itself. And then we can drag the player outside of this, outside of the range, just so it doesn't trigger automatically. We can watch it fall. And then once we have that set, we also want to set this to a trigger, because we don't want the player running into it. We want the player to be, for it to recognize that the player is within the boundaries of the door. Now we added the trigger, and Unity has a built-in method where we literally don't have to do anything. It already built all of it for us. All we have to do is call the method private void on trigger enter. And then we have another collider. Whenever another collider bumps into this, we want to rebuild the door, right? But we don't want every other collider. We just want the player collider to trigger that event of rebuilding the door. Let's go ahead and do a check. We're going to do if other.compare tag, and compare tag is just going to grab the tag of this, and we're going to check like what this tag is. Is it going to be untagged? If it's player, is it going to be player? Usually you don't want to work with strings like this, but this isn't a really big deal. And if you really wanted to make this better, and you're still working with strings, but it's slightly better because you're holding this inside of a const, you can do private const string, and then we'll say player tag, and then we'll set this to player. And very important, whenever you do a const, or you have to assign the value of the const immediately. You cannot separate the declaration and the assignment away from each other. So now that we have our player const, we can do player tag. So if ever in the future we need to change the player tag, we can just go up here and change it from here, instead of going through all of the code and trying to find that reference of where did I write player, you know? So it's a lot simpler to work with, but realistically, we shouldn't have to do that. So now that the player has entered the trigger area, we want to rebuild our door. So this rebuild our door is going to be probably the most complicated piece of this video, because we want each piece to slowly go to its original position. But like I said, right now we have the problem. So they're all going at different times. So we don't really know how long each of them it's going to take in order to finish completing rebuilding the door. So we're going to have to make sort of like a method to add onto each individual rigid body and like rebuild that door by itself. I don't know if that makes sense. So rebuilding the door is going to be the most complicated part, just because we want to go through each individual rigid body and then apply it back to its original position and rotation while having an offset. We can do that inside of a for loop. So let's go ahead and see what that loop would look like. So we'll write for, and then we're going to get I is equal to 0. See, we're using a lot of for loops. We're doing I less than rigid bodies dot length. And then we're iterating through them just one at a time. We're going to want to rebuild each door piece, and inside of rebuild each door piece, we're going to want probably a couple of things, right? We're going to want the rigid body so we can turn the kinematic off. And the great thing that we already have our rigid bodies and we're already iterating through them. So we're going to get rigid body I, and then we also want to get in our initial position. And because all of our arrays are the same length, we assigned each of the arrays per child. Everything should line up without us having to do anything. So if we just look at initial positions and then we go through I, that should be the correct position for the child. And then we also want our initial rotations, and then we want to put that inside of I as well. So this is going to be the 3 arguments that we provide and into this rebuild each door piece. So in order to rebuild each door piece, we're going to do a private void of rebuild each piece, door piece. And then we're going to get one is going to be the rigid body, rigid. Another one is going to be our vector 3 of our position. This is going to be our end position. And then another one is going to be a quaternion. This is going to be our end rotation. But we cannot set this all inside of one frame. We have to set this over the course of multiple frames, and we can't really do that with a regular method. So we have to use a thing called coroutines. Coroutine just waits for a certain specified amount of time in order to execute a function, and then it will execute that function once that specified amount of time has been met. So in order to turn this into a coroutine is not too difficult. The coroutine is we're just going to name this enumerator. And now this will throw an error, and it's saying that we can't, the return value is not used. Coroutine will continue if return is ignored. We have to return something, but we're like, when are we going to return it? What are we doing? Let's just figure out what we want to do first and how we're going to iterate through that over multiple frames. So the first thing that we want to do is we want to track the amount of time that has elapsed, right? So right now, elapse is going to be equal to 0 because no time has elapsed in the very beginning. We also want to get our transform dot our rigid transform. And the reason why is because we're going to get the rigid body and we're going to apply the changes to the transform directly. So in order to get the rigid body transform, you just go to rigid and then you just get the transform. Really simple. We also, in order to interpolate between one point and another, we can use something like vector3.lerp. But if we use vector3.lerp, it will sort of, because of the way that vector3 lerps work, when you don't have a stationary start position, it will slowly start to ease into the end position value, and it sort of doesn't really care too much about the time that has elapsed, because C# works off of a programming language, C#, that doesn't have like an infinite amount of space when it's calculating floats. So I think it's something like 52, after 52 iterations, it should, or some number like that, it should already be at its position. So in order to actually properly use lerp, we have to keep track of a start position. So in order to do that, we're going to keep track of our start position, and that is just going to be using our rigid transform dot position. And then we also want to keep track of our start rotation, and that's going to be rigid transform dot rotation. We have our start and end for both our positions and rotations, and the end position is going to be provided to us when we initially set it up here. Now what we want to do is, like I said before, we want to turn on the kinematic because we don't want our rigid body to be fighting against the Unity engine's physics calculations while it's being moved. In order to do that, we're just going to do rigid.isKinematic, and we're going to set this to true, so it does not interact with anything. And now that we have that set, we want to actually go through a loop and transition all of these positions of the rigid transform from the start position all the way to our end position. In order to do that, we want to get the duration of how long we want this enumerator to run. In order to do that, we just have to add a new method of what is our duration, like how long do we actually want this to run. And now we have to provide that duration inside of here. But like I said, we want things to be slightly offset. So we can add a serialized field for a private float, and then we can set this as rebuild duration. But we also want a serialized field for another private float, which is going to be our rebuild duration offset, just one F. And now to get our duration of how long we want each door piece to be rebuilt, all we really have to do is just calculate a random, or we just have to get a random value between the random duration plus the random duration offset, which should be pretty simple. We've done it already 3 times over here. So we're just going to do that again. So we're going to get our random duration. We're going to equal that to our rebuild duration plus our random.range. And we're actually going to set this as 0 in the beginning because we want it to be only additive rather than subtractive. But if you wanted to do it subtractive, you could also do that. You'll just have to make sure that your rebuild duration is more than your rebuild duration minus your rebuild time offset. But you can do it if you want. I think this is simpler to just have the offset be an additive value and not a negative value. And now we have our random duration, and we can pass this inside of our coroutine. And you can see that this is still throwing an error, and we'll get back to that because this does not return anything yet. Now that we have that, we're going to write another loop, and this is going to be a while loop. And while our elapsed time is less than our duration, then we want to continue to go through our loop and try to position our pieces in a way that makes sense, right? So the very first thing that we want to do is we want to get the elapsed time and then just add time.delta time. Now you may be wondering, if it's all running on the same frame, how exactly are we going to get time delta time if the last frame is just going to be adding the last frames between the delta between the last frame and this frame? And the reason that how we're going to do that is actually by using the whole reason why we're making this inside of an I enumerator is to have that feature of spreading out this logic over multiple frames. And I'll show you how to do that in a little bit. But let's just do the calculations, everything we want to do. So in order to get our completion value, this is going to be equal to our elapsed time divided by our duration. So if it's like half a second and we set it to 1 second, then our elapsed time is going to be 50% done through the interpolation of our lerp or linear interpolation or slurp, right? So this is just the completion value of where our transform should be in that interpolation of these two values of the start position and the end position. Now, in order to actually set that, all we have to do is get the rigid transform and then get the position. And then in order to get the vector 3 of where we want this to be, we just do vector 3 dot lerp, and then our start position, our end position, and then our completion value. And that's pretty much it. The problem with this is that when you have it set like this, the start position and end position, the entire thing will be very linear. So it'll start really fast and then it'll end really fast. It'll just like abruptly come crashing into the end, and it'll just like snap into position basically. And so we don't want that. Instead of doing lerp, I think slurp is actually a better interpolation method for this, just because we get that easing factor from the start position into the end position. And we basically want to do the same thing with our rotation. Rigid.transform.rotation is equal to a quaternion dot lerp. We're sort of having that same issue of, well, don't we want it to sort of like smoothly go into the position? You can if you want to, but I find that a lot of times the rotation of the boxes actually are not that significant. So you sort of lose a lot of movement near the end if you do want to do a slurp, because it eases into the end position, right? So you get a lot of movement in the beginning and then not a lot of movements at the end. So it sort of feels like, wait, it stopped rotating before it even got to its position. After experimenting, I feel the rotation value can be used using a lerp, but you can experiment with that. You can change it. It's literally one letter, right? Or two letters. Change it from a slurp to lerp. Okay, and then we get our start rotation, and then our end rotation, and then our completion value, because it should be the same how long it takes to turn it and to get it into position. After this, we also want to make sure that the position is the exact same for all of them. Like, we don't want it to be slightly off, which can happen because we're working with float values. We're not working with real life precise, like infinitely precise numbers. We're working with float values that go down to like, I think 8 points. So in order to get everything set exactly perfectly right, we're going to get the transform of each position. So we're going to get our rigid transform, and then we're going to get the position, and we're going to set this as our end position. And we're going to do the same thing for our end rotation, just so it sort of snaps. So if there's any minor deviations, we can just ensure that it is in its final position by just setting it at the very end. And this is going to avoid any like little cracks or anything that you might see if it's a 3D model and you see like light leaking through. This is going to avoid that, just so we can set, okay, we're setting it. The big thing that we're waiting to do is, like I said, this is going to add the previous frames delta and the current frame delta onto the elapsed time. But if we're just calculating this all on one frame, how is this possibly going to work? How are we going to spread this out across multiple frames? And the way that we do that is by doing a yield return inside of here. So we do yield return, and how you would initially write this is you would write something like new, wait until, wait while, wait for seconds, or wait for fixed update. So probably the one that probably makes the most sense for us is wait for end of frame. And we can do this where it will just wait until the end of the frame to actually run the next calculation. And since we're doing it inside of a while loop, it will just wait till the start of the next frame to do the rest of the loop. And then again, the start of the next frame to do the rest of the loop. So we can do it this way, and this way is perfectly fine. But another way to write this is by doing yield return null. And the reason why this is going to essentially do the same thing is because it is still waiting till the end of the frame in order to see how long it should wait. So if you do yield return wait till end of frame, I'll go like, okay, I have to wait till the end of this frame in order to start calculating the next position, right? Or to continue doing the logic. If you add in yield return new wait for seconds, and then you put like 10 seconds right inside of here, it will wait till the end of the frame to check how long it should wait again before running through this function again. So it's still waiting till the end of the frame, but then it's adding 10 seconds onto that time. So if we just return null, it's going to wait till the end of the frame every single time until it runs the next piece of code. This basically allows us to run this code over a period of time instead of just running it all on a single frame. Now it's still throwing an error up here, but this is no longer throwing an error. There's no more squiggly line. Now the reason why is because we cannot call an IEnumerator directly like this. In order to call an IEnumerator, we have to add this coroutine inside of another method as an argument, and that method is called start coroutine. And then we just add the comma at the end, and that's it. And now this is functioning exactly how we want it to function. However, there is another problem. If we enter this, whoop, should it be working? Don't know why it's not working. Maybe we put the string wrong. Did we not write player? Nope, player is written correctly. Okay, the reason why it's not working is because we forgot to put on the door summon script on top of here, and we want to add a random force in the beginning, something like 5, and I have the values from over here. So what I chose initially was 2, 0.4, and 1, so we can do that. We'll just do 5, 0.4, and 1. And now if we run into this door, whoa, look at how big it exploded. You see? It'll go back. But if we exit, it's not rebuilding itself. Or it's not destroying itself. So the only thing we have to do in order to add that feature is we just do the same thing again as the private void enter. So we're going to do private void on trigger exit. And we're still going to check if this is the player, because we only want the player to be the one to be able to interact with this tag. And then once this is here, literally the only thing we have to do, really simple, is just call the destroy door method. Okay, we enter, go back, should be working perfectly. Except we're getting a little bit of some weird behavior. You see how some of it is moving, but some of it isn't still after? It's getting this kind of weird like behavior. You can see some of it jittering a lot, you know? A lot of it is really jittery. So this is some weird behavior, and it's not present in this other one.
Okay, the reason why we're getting that jitter is because the Unity engine is fighting against two separate forces that are trying to move the the each individual rigid body. And you'll notice when we get close that if we start to do it until after, yeah, we have those some are still moving up, some are still moving down, and then we have this jitter because we have two different forces being applied to each individual piece. One of them is going to be the rigid body itself, which is trying to pull the objects down, and then our code, which is trying to raise these boxes back up to their original position. So the way we can stop that is really simple. The reason why it's happening is because of this code right here. This code has not finished, completing. So we just have to tell our code that whenever we destroy a door, if there is a coroutine running, to stop that coroutine. Now, there's a couple of ways we can do this. So I'm going to show you the easier way. One way is to keep track of this coroutine and just have that set as a variable, and then we can call stop coroutine if this coroutine is running. The other way is a lot simpler, is we just call the method stop all coroutines. Now, if we do that, when we first destroy our door, if we have a coroutine running, it will just stop that coroutine and we won't get any of those conflicting movement logic ideas. So now if we go back and then we leave, you'll see that it immediately falls to the ground, right? There are no more objects that are trying to get raised back into position. Everything is just working perfectly fine. But you will still notice that there is a slight amount of jitter on the boxes. And the reason why there's a slight amount of jitter is because Unity has their own physics engine that actually runs on a fixed time increment. And we could go ahead and check that by going into our file, build settings, player settings. And if we go into physics, you'll see that we have our simulation mode set to fixed update. You may be wondering, how fast is this fixed update? We could just go to time, and then you'll see right here our fixed time step is at 0.02. So every 0.02 seconds, we will calculate some physics. So there's a couple of different ways that we can solve this this issue, and probably the one that makes the most sense would be if we go through all of the boxes, and then we set them to interpolate. So in order to do that, we go to interpolate, and then we set it to interpolate. Interpolate just means that we're having the start value and an end value, and extrapolate is we have the start value, and then we also have the velocity of where the object should end up going, and we want to plan ahead of where we think this object is going to go. For our case, I think interpolate is fine, and if we click on play and we watch, you'll see that when it's being destroyed, it is a lot smoother. So now if we check, you'll notice that they don't always end up in the correct position when we set it to interpolate. But we do solve the problem of it falling down and it being a little bit jittery. But again, especially if you have a 3D model, it not landing back in the exact same position is not a great thing, right? Because then we're going to have some light leaking through the 3D model, and it's just not good to have that, right? You can see this box is out of alignment. It looks like some of the top boxes might be out of alignment, and it's going to be random every time. This time it's fixed, but then we have this box in the corner that's not fixed. So in order to solve this, there's a couple different ways. What we can do is, my original idea was just to have another yield return null over here, yield return null, after the loop finishes, so that after everything is done, we wait a single frame to try to place everything back into the correct position. But if we do that, we're going to have another problem. You see that we have a little bit of jitter when it goes back into position with pretty much all the boxes now. And we still don't actually solve the main problem of things being out of alignment. So this solution doesn't work. The solution that actually does work is in order to allow these boxes to go into position when it's getting rebuilt, we just set this to none. But when we want the box to be destroyed, we set it to interpolate. And we can do that really easily. So whenever we destroy our rigid body over here, instead of just setting it to kinematic is equal to false, we set our rigid, and then we set interpolate, and then we set this to rigid body interpolation dot interpolate. Now this is going to set it so whenever our door is destroyed, that it will start to linearly interpolate between these two start and end positions. But over here, we don't want it to do that because then we have that misalignment that we've been seeing. So over here, we just set the interpolation mode to none. And now once we have this set up, we have interpolation set to none and interpolation set to interpolate. We should now see that all of our issues are fixed. We go back in and everything lines up perfectly. We leave and we don't have any of that jitter anymore. Go in perfectly, leave, no jitter. And that is how you would set up something like this, like the God of War door. If you want a part 2, I already have some ideas of how we can expand on this. If you're curious about how, like, what if when the door is completely rebuilt, we want a portal to open up so the player can walk through. How would we handle that? Another problem that you might have if you have a 3D model is that sometimes you will have multiple objects inside of one object like this. And how would we handle this? And let's say that for some reason you can't add a rigid body to every single one of these. How can we do that in code? Now, some of these answers are a little more difficult and easier than others. So if you want to see a part 2 just talking about different ideas and how you might want to see this being improved, let me know. But for now, this has been your dev dog signing out. Riff!